Hello, my name is Karl Jukic, and this is Physics Lab 4. Our introduction for this lab is that the purpose is to observe and measure a swinging oscillating mass on a spring using experimental and model data. Models will be using our Newton's second law and the energy principle. The main result is that the computational model and the observed data were similar but did not match completely, most likely due to calibration error. Fundamental principles are Newton's second law. Objects in motion will stay in motion unless acted upon, where F net is equal to ma, and change in momentum is equal to F net times delta t. The energy principle, where the change in energy is equal to outside work. Or kinetic energy is equal to mass times velocity squared over 2. Gravitational potential energy is equal to mass times acceleration due to gravity times the height from the Earth's surface. Spring potential is equal to the spring constant times the stretch or compression distance of the spring squared over 2. For our lab, I used the non-sample data by calibrating my own spring. Our system here is the mass on the spring, and the Earth, where our surroundings are none because we're trying to account for all energies. Initial conditions is that it's a 200 gram mass. Our initial velocity is 0, and we have that initial position at the bottom right. The calculated spring constant from the two measurements I used was 8.3, and our L naught was 0.1233 meters. For our code, here we have our listed initial conditions, where our ball mass, our initial position, and our delta t, which is very small as the video says 30 frames per second. Gravitational constant, our calculated spring constant L naught, and here we have our lines to specify the directions and lengths of our spring, where the L is just the distance from the fixed point of the spring, which is set to the origin. Our L hat's direction, so it's just the distance over the magnitude, and our compression distance is the length minus the current length of the spring minus its resting length, which was already calculated. These are energy listed, which is our kinetic listed earlier, our gravitational listed earlier, and our spring listed earlier. And all of our energies will come up to just all of these added. Here we have our list that makes the code run. We list our gravity as the gravitational force, our spring force, and our F net is just the two forces that are acting together. Here we have our Newton's second law, where velocity is acceleration over mass times delta t, and our position is the changing velocity plus initial velocity. We define our spring stuff, and then this is all for show, where this is just calculating a calculation loop for each step. For our models, we were given out this x position graph and this y position graph. Our simulators at the x and y position are close to our observed data, where obviously blue is the model, red is the experimental. And our total energy change is near zero, where it should be. Differences is that our offset oscillation times, especially in the y direction, and that the oscillation magnitude slowly decreases over time. As you can see here, they're kind of close. At the end, this x magnitude is a little bit further from the model data. Some errors, especially for the distance, is either our delta t set it was off, as I was having trouble earlier trying to get these graphs to align, and most likely calibration error when trying to measure our spring constant and resting length of the spring, and drag resistance not accounted for in the model, which is accounting for the differing oscillation magnitude. So what does it mean? Is the energy principle satisfied? Here we can see it is almost satisfied, as we account for all the energies acting on the spring, so the work should be zero. Um, there are small fluctuations, but this can be accounted for the force of drag, seeping out energy of the system, as well as improperly calibrated spring force, as the modeled spring force is not accounting for all of the energy it was actually using in the data. For what does it mean too? We provide two separate estimates of oscillation periods, which is just the period to complete a full oscillation, from the x position and the y position. When we look at the experimental data, we can see that the x period is roughly about 1.2 seconds, and our y period is roughly about zero point 0.8 to 1. It fluctuates depending on the position of the graph. This period is most likely due to incorrectly calibrated spring, as the most discrepant period is the y period. And that is the direction where the majority of the spring force will be acting in the experiment.